In this segment, I'm going to discuss two examples of the Fourier integrals. So first is going to be the top hat function. So what is the top hat function? So the top hat function, let's start with the k space. So let's take a function in k space. So a of k is going to be some constant, which is 1 over square root of epsilon, where epsilon is a positive number, for k is less than or equal to epsilon by 2, greater than or equal to minus epsilon by 2. And it's 0 otherwise, right? So, what does it look like? It looks something like this. So if we just plot this, this is k, this is just going to be something like this, where this is epsilon by 2, this is minus epsilon by 2, and the height of this guy is 1 over square root of epsilon. So then we ask, what is the Fourier transform of this function? So the Fourier transform of this function, psi of x, will be given by our formula for the Fourier integral. And of course, this is because this function has a limited support, the integral from minus infinity to plus infinity is going to reduce to an integral from minus epsilon by 2 to plus epsilon by 2. So we can just write that out here. And and what is a of k in that range? A of k is 1 over epsilon square root of epsilon, and then we have our function, and then we have to integrate it over dk. So this is a very easy function to integrate, and if you do that, when the dust settles, you get 2 by pi epsilon square root. Then you've got the sinh function. Sinh function is given as sine of x by x. And of course, this may look singular at x equals to 0, but it's not, because when x is very small, the sine of e epsilon x by 2 is just epsilon x by 2. So when x is very small, these two x's cancel out, and so this is completely regular at x equals to 0. So if you haven't seen the sinh function, you should have a look at it. So this function looks something like so it looks like a little bit like a kind of a cosine wave that's dying out. But what's interesting is that the width of this middle bit, the fat bit, which we can associate as its spread, is 4 pi by epsilon, whereas the height is square root of epsilon by 2 pi. Okay. So one thing to notice is that for the top hat function and the sinh function, we can look at their width, look at their spread, and we can multiply them. And if you do that, then we get, I think it's 4 pi. But what's important is that this is a kind of an order 1 number, maybe order 10, but it doesn't matter the precise value so much. But it doesn't depend on epsilon. So see that if I make my top hat taller and thinner, so basically what I'm doing is that I'm reducing epsilon. What happens is that my sinh function becomes fatter. So the thinner this becomes, the fatter this becomes. And in a way such that the spread, the product of the spread of these two guys doesn't depend on epsilon. So this is kind of an important observation that will have physical consequences later on when we talk about quantum mechanics. And there's also a theorem that we will prove later on in the course. So from Parseval's formula, we can see that, the integral, this integral is very easy. It's just constant. And it's normalized in a way such that we just get 1 here. So it must be true that this is also equal to minus infinity to plus infinity of psi of x squared d of x. So although this first integral is trivial, the second integral is not. So the second integral implies that 2 by pi epsilon integrated from minus infinity to plus infinity of the sinh squared of epsilon x over 2 divided by x squared is 1. So this doesn't look like an easy integral, but one can do. So anyway, we're not going to do it here, but in the next section, I will show you how to do this integral using contour integration. So now we want to relate. What we have done is that we have shown how if I start with a of k, I can derive the expression for psi. What happens if I start with the expression for psi? Can I derive the expression for a, which we already know? So this, of course, will be given by the other Fourier transform formula. And this is given by square root of 2 pi. And then you have from minus infinity to plus infinity, the sinh function doesn't die out very rapidly, not like the top hat rapidly, but not that rapidly. So we have to, in principle, take the whole limit. And then we have here sine of ex by 2 divided by x e to the power I kx d of x. So this is an integral which can also be done using contour integral techniques. And I'm actually not going to do this in this lecture. So I'm leaving this as an exercise for you to do. So you have to do this by yourself. And so that brings us to the end of our first example. So our second example is going to be about the Gaussian. So next we are going to take psi of x is the Gaussian, and here we have some normalization, sigma square root of pi e to the power minus x squared divided by 2 sigma squared. So the Fourier transform of the Gaussian is also another Gaussian, and you can show that. And to show that, you need to do, of course, the Fourier integral, and there is a crucial step there that you have to do an integral, and I will be showing you what the crucial integral is in the next video. So anyway, so the Fourier transform of the Gaussian is another Gaussian, but this Gaussian has different kinds of normalization, and its spread is also different. So let's look at these Gaussians. So the first one, which is psi, sorry, let me redraw that. So we have a Gaussian like this. So this is psi of x, and we can, define the width of the Gaussian to be that we, to be that determined by the cutoff where the height of the Gaussian, the height of the function psi of x falls to 1e of the highest height. So on both sides we can define it like that. If we do this, then the width is going to be given by sigma. On the other hand, the width of the Fourier transform is going to be given by 2 square root of 2 divided by sigma. So here we see again the kind of phenomena that we observed in the last example, which is the width of the function and its Fourier transform is of the order of 1. In this case, I think it's 8 or something, but it doesn't depend on the spread of the Gaussian. It doesn't depend on sigma. So that if this becomes thin, this becomes fat, and vice versa, right? So if this Gaussian becomes very, very narrow, this becomes very fat, and vice versa. Okay. And of course, one can verify that so one can verify that Parseval's formula holds, of course. And to do these, to derive these expressions, one needs to do what is known as the Gaussian integral, and that will also be covered in the next segment of this lecture.